It's only in the global experiment that we've been undertaking in the last 50 years or so in which we've begun to replace this legume-based nitrogen with synthetic forms of nitrogen that we've started to see some of the problems that arise as a consequence of that switch. But legumes remain fundamentally important to our agricultural systems in all sorts of ways. We grow forage legumes, we grow grain legumes, we grow intercropped legume systems. And I want to examine some of the ways in which legumes contribute to our current agricultural production and think about ways in which we could optimise that. So I'll still start off with a bit of doom and gloom of my own before I get into the optimism. So we have problems in terms of lack of forage protein in our production systems, particularly in Europe. We've seen problems associated with increasing costs of energy, which are linked, of course, to fertilizer manufacture. We've a lot of problems with emissions of greenhouse gases and other substances from agriculture we've talked about this morning. Problems which will probably restrict resource input to systems. And as we've talked about as well, with this growing demand for meat and milk. Challenges that are all very relevant to the way in which we use legumes in our production systems. Now, despite our increasing use of fertilizer nitrogen, global production of legumes has increased very substantially in recent years. These are the grain legumes that we produce globally, but they are dwarfed, those peas and beans, incidentally, that are produced globally. The production of those is dwarfed by the increased in production of soya on a global basis, and that top right graphic shows you that global increase. And that increase has been provided in order to feed our global livestock production. But it's been done in a way that disconnects production and consumption of products on a global basis, and that disconnect has led to a large international trade in reactive nitrogen in the form of fertilizer nitrogen, grain-produced nitrogen in proteins, and meat itself. So, for example, we see a massive export of soybean from Southern America into Europe and China to support the livestock industries that have been developed there in this disconnected agricultural system that we've developed since the reduction in use of, or since we've become more dependent on the use of synthetic nitrogen fertilizers. However, nitrogen fixation remains an important process in our agricultural systems, so this is some work we've done recently to try to improve our estimates of nitrogen fixation in Europe. We get nitrogen fixation in peas and beans, but we also have significant amounts of nitrogen fixation in forage-based crops, and the green bars there represent the forage-based crops. So UK, France, for example, have significant amounts of nitrogen produced by forage crops. And you can quantify these amounts contributing to quite significant equivalent fertilizer values in Europe. However, these are relatively small by comparison to the total amounts of synthetic fertilizer that we currently use in Europe, about a tenth of the amount of synthetic fertilizer that we use. So are there opportunities to change this balance? Well, Patrick talked this morning about the way in which we've used fertility that's built up in grass, forage-based systems to feed arable cropping systems in mixed rotations. And this is something certainly traditionally agricultural systems have depended on for many hundreds of years. As I say, this has started to break down now in the way that we've changed our agricultural systems. But there are still many systems that depend upon this cyclical and rotational approach to fertility management, building fertility during a grass forage phase of a rotation, and exploiting that fertility during a cropping phase when we have cereals. And this is still the basis of many systems of agricultural production on a global basis. We can understand better how to optimize that system by going in and making measurements of the way in which that nitrogen is cycled and obtained. So these are measurements, for instance, in a rotational system that we've made of the inputs of nitrogen fixation. And I think this information helps us to try to optimize and balance the system. So two things that you see, well, a number of things are important about this diagram. Firstly, that there's quite significant amounts of nitrogen coming in from a clover-based ley. Secondly, that that input of nitrogen varies according to the age of the ley. So as the ley gets older, the amount of nitrogen fixation reduces. And the amount of nitrogen fixation over the period of a year during the course of the summer actually declines as well. And there are influences of soil properties that impact on that. But I'm going to focus a little bit on the issue of legumes and greenhouse gas emissions, because this is one of the topics for discussion today. And one of the issues here is that legumes tend to produce nitrous oxide emissions, greenhouse gas nitrous oxide, in a different way to conventional fertilizers. And there are two ways in which they do this. The legume, which is associated with symbiotic bacteria and its root, produces nitrous oxide by those bacteria themselves. The bacteria are able to produce nitrous oxide directly. There's also an emission associated with the decomposition of the plant material that is produced by the legume. But the issue is that leguminous crops tend to produce less nitrous oxide than is produced by other types of comparable crops. So this is a survey of large numbers of experiments which have looked at different systems producing grass, cereals, legumes and so on, show that legumes, these are actually grain legumes, but the forage legumes come even lower down, produce something like a third of the amount of nitrous oxide that are produced by grass crops. And let me just think about, just for a moment, the sort of conventional production of grasslands. So here's some experiments we've undertaken looking at the impact of the addition of fertilizer on nitrous oxide emissions from a conventional grassland using different rates of fertilizer application here. And this is a measure of nitrous oxide emission. So as you increase the rate of fertilizer application, you increase the nitrous oxide emission. The red bar in this diagram represents the sort of standard agronomic practice. If anything, the relationship here is almost non-linear, so going above the standard agronomic practice is a particularly bad idea because the emissions rise very steeply. The emissions that we see in this sort of system were comparable with the sort of standard emission factor that we would measure, but the interesting thing is that the yield response to fertilizer is very different to the nitrous oxide response. So the yield response down there in the bottom right is fairly flat at the sort of higher rates of nitrogen application, although the nitrous oxide response is increasing very steeply, which has interesting implications for yield intensity calculations. So why do legumes produce less nitrous oxide than conventional crops? Well, there are probably a couple of reasons for this. In forage legume-based systems, grass clover systems, part of the reason is that the nitrogen which is being added to the soil is coming in and being spatially distributed quite widely throughout the volume of the soil. There's also a gradual input of nitrogen over time, as opposed to synthetic fertilizers, which are added in large quantities in sort of at the surface of the soil, so have very high concentrations, promoting potential loss. But of course, as always with these things, there are subtleties to this, and we're beginning to understand some of the complexities of it, which are really helping us to understand the way in which we can modify systems. So, for example, there's a nice bit of work that's been published recently from a Japanese research group, and there's some French people looking at this as well. They've actually looked at the role of the Rhizobium bacteria in contributing to nitrous oxide emissions. So there's a gene called NOS-Z, which creates an enzyme that reduces the nitrous oxide molecule to dinitrogen. And we can use varieties of clover that have the rhizobium with more of this NOS-Z gene in it and look at the impact that would have on nitrous oxide emissions. So the blue line here represents nitrous oxide emissions from a standard rhizobium species, and a modified species there with the red and yellow lines has a lower emission. So the suggestion here was that these sorts of modifications to the Rhizobium species could actually be used even to remove nitrous oxide from the atmosphere, although I suspect the potential for that is quite limited. The other part of emissions from legumes is the crop residue, and this is a lot more uncertain. We assume that residues of legume species emit nitrogen in the same way that the nitrogen inputs from fertilizers do, so an assumed emission factor of 1% is used in calculations. But it is very difficult to measure this, and some of the studies that we've been doing recently suggest that that emission factor may be too high. But management of residues and understanding that residue decomposition, I think, is an important priority for research. But having said all this, I think there are opportunities to bring together the use of fertilizers and legumes in farming systems. So this is a nice bit of Swiss work that's been undertaken by Andreas Luscher's group in Switzerland, where they've looked at using nitrogen fertilizers in combination with legumes in pastures. And they've added different amounts of fertilizer nitrogen to a system. Of course, if you don't have any legumes present, the amount of yield you get in response to increasing fertilizer, as I've shown, increases very substantially. But the interesting thing is that when you put legumes into that system, that responsiveness to the nitrogen fertilizer starts to decline. And a pasture fertilized with just 50 kilograms of nitrogen produces as much yield as a pasture with no legumes in it, fertilized at 450 kilograms with nitrogen, if you have about 50% legumes in your mixture. So far I've talked about nitrous oxide only within the farm gate, as it were. I think it's also just important, before I finish, to mention some of the wider life cycle analyses. Biological fixation of nitrogen uses energy from sunlight, whereas production of nitrogen, synthetic nitrogen, requires an external energy input, fossil fuel equivalent of 2.25 kilograms of CO2 per kilogram of nitrogen fertilizer, and a further emission associated with nitrous oxide production. That figure is probably higher than best standard practice at the moment, but nevertheless, the emissions can be quite significant. So, very brief overview, but let me just summarize. Legumes have and still do play a critical role in supporting agricultural production in Europe and at a global level. We know that the greenhouse gas emissions associated per unit of nitrogen input associated with biological fixation are much lower than those associated with synthetic nitrogen, partly as a consequence of more efficient use, but also avoided manufacturing emissions. There are opportunities to improve the design of systems which use forage legumes, and we don't need to switch to legume-only systems. Combining fertilizer with legume use I think is an important and overlooked opportunity. And there are still more things that we need to understand. For example, as I've mentioned, the importance of residues in contributing to emissions, and also the interaction between N-fixation and carbon sequestration, which is something we really know very little about. Nitrogen has an important controlling role in carbon sequestration. There are relatively few studies that have looked at this nitrogen fixation impact on carbon sequestration. So I'd just like to finish there and thank the funders, numerous funders, for supporting this work.
Thank you, Bob. And our final speaker for this morning is Mike Wilkinson. Mike is a special professor at Nottingham University, and I am now a generous chairman, apparently. Let's see.
Thank you, Mr. Chairman. Thank you, Richard, Patrick, for the invitation to speak here. I make one point, and that is looking at typical livestock diets, the composition thereof. Ruminants are as efficient as, and in some cases more efficient, than non-ruminants, pigs and poultry, at converting potentially human edible feed resources into animal products. I could stop there, Mr. Chairman, but I won't.
Carry on. I hope the rest of it is good, of course, but otherwise we might wish you'd stop there.
Gets better.
Good.
Gets better. We're talking here about the feed conversion ratio. people ask the question, how much grain does it take to produce a kilogram of meat? And the general agenda behind that is that it takes a lot. Too much, far too much. Pete Smith's already mentioned the 30% of the world's arable crops that go down the throats of livestock. But we need to consider what we're talking about very carefully. We need to define the numerator. It's a ratio we're talking about, so we need to define the numerator. What are we putting in? What's going? What type of feed? Is it fresh weight, dry matter, concentrate, energy, protein, or what? We also need to consider the denominator, the animal weight, the weight of the animal, the whole animal, its energy concentration, its protein, its amino acid profile, as Michael Lee has mentioned. And we need to consider the context, the system of production, the type of land, the breed of livestock, and so on. If you think the shape of this graph looks familiar to you, you've seen it already once in Pete Smith's contribution, where the ordinate was greenhouse gases per kilogram of product. This is 10 typical livestock systems, Northern European livestock, Northern European livestock systems. Upland, if you can't read the writing at the back, upland lamb, lowland lamb, reading from left to right, upland suckler beef, lowland suckler beef, dairy beef, that's calves born in the dairy herd reared for beef, cereal beef or barley beef, milk, pig meat, poultry meat and eggs. Based on a paper published in the journal Animal in 2011. The output is defined as whole milk in the case of milk production, bone-in carcass, fresh weight, or egg plus its shell. And this is the total dry matter in the diet per kilogram of animal output, in this case carcass weight for lamb. And you can see these big blue lines illustrating the reproductive cost of maintaining a breeding female all year, and this is what gives Pete Smith's figure such a high number. Maintaining a breeding female all year just to produce a lamb, a lamb and a half, or 2 lambs, Chris, or maybe a few more if you're lucky, or 1 calf, or 0.9 of a calf per cow in the case of Richard's beef system. Milk does very well for 2 reasons, because milk is largely water, and also the breeding female is also the productive unit. But if you look at the red bars, this is the amount of concentrate that these livestock systems use per kilogram of product. And when you look at concentrate conversion, the numbers are much closer to each other. The one that sticks out, of course, is barley beef. By definition, the diet is very largely cereal grain. But the ruminant systems compare more favourably. If you then go on to divide up the concentrate into the proportion that is inedible, so take the whole diet and look at the proportion that's inedible, grass, straw, food industry wastes, and this is where we're getting more relevant to the African and Asian systems of livestock production, industry waste and byproducts, and divide up the diet in that way between the inedible bits and the edible bits, cereal grains, pulses, soybeans and so on. You then start to look at typical concentrate formulations. This is again from Northern Europe. Dairy cows get relatively little grain in their concentrate formulations. I'm sure Patrick would agree with me that his dairy cows don't get a lot of grain in the concentrate, the limited amount of concentrate that they get.
Do you want me to comment on that?
No. Because you're not nodding your head.
In a minute.
Later. Where you get to laying hens and broiler chickens, the proportion of grain and soya is a very high proportion of the total weight of the concentrate fed to those animals. So then we're looking here at energy conversion, and the graph looks similar to the previous one. And when you start to look at the edible energy conversion, remembering that grass is inedible, silage is inedible, cereal byproducts are considered inedible, then the ruminant systems perform as well, if not slightly better, than pig meat and poultry meat and eggs. And where you see a number there, it means that we're getting more out than we're putting in. So we get more milk energy out than human edible energy going into the system. And the same thing is true for protein. And here upland beef, upland suckler beef, is more efficient, more out than you put in, as is milk. And these green bars are slightly lower than the pig meat, poultry and eggs. So the ruminant does relatively better on this analysis. So in conclusion, Mr. Chairman,
Well done.
ruminants have a special ecological role as efficient fibre digesters. They're less efficient converters of total feed into animal product compared to pigs and poultry, but most of the ruminants' diet is not edible by humans, and that is particularly true in countries like Ethiopia, where byproducts form a very large, if not the whole, diet of the animal. Ruminants are as efficient as pigs and poultry at converting human edible feeds into milk and meat. Thank you very much.